This is lesson 5 on page 32 in your booklet, and we're looking at rate of change today. So this is where the word problems come back. So we've given this little formula that the rate of change is the change of the dependent variable divided by the change in the independent variable. Now, in the world of x and y, the dependent variable is almost always y, and the independent is almost always x. So another way to think of this is that it's really analogous to the slope, because the slope is your rise over run. So if you have rise over run, really what you're looking for is your change in y over your change in x. So the rate of change is a slope. It's just a slope with a word problem. So here's an example. This graph shows the temperature in a location over a 12-hour period. So it starts in like a very cold temperature, and then the temperature starts to go up. So it says state the vertical and the horizontal intercepts. So normally the vertical intercept is your y-intercept, but in this case it's t, temperature. So the vertical intercept is here. But if you read carefully, every box represents 2. So this is not 5, it's -6. So the vertical intercept is -6, and you have to put a unit on it, degrees Celsius. And what about the horizontal intercept? Well, the horizontal intercept is wherever it hits the x-axis here, but in this case, it's the little t axis. So over there, it looks like 4. But because we have a word problem, we have to put hours on it. So this is 4 hours. Okay. So what do they represent? Well, -6 degrees is here, where it's -6 degrees at hour 0. So -6 degrees represents, I should have drawn this over here, the starting temperature. Because time is 0, but the temperature is 6 degrees. Okay, so starting temperature was -6 degrees. What about this 4 hours? Well, what are the coordinates of this point here? It's 4, 0, as in 4 hours, but 0 degrees Celsius. So 4 hours is the time it takes for the temperature to get to 0 degrees. Okay, so we're interested in these vertical and horizontal intercepts and as well as what they mean. So determine the rate of change. So the rate of change, as we understand it, is the slope. So we're going to pick a point that's easy to read. Let's say this one. And it's at 12 hours, 12 degrees Celsius. And we're going to pick this one as well because it's pretty easy to read. So if you read your rise and your run here, we're looking at a rise of 12 degrees Celsius. And we are looking at a run of 8 degrees Celsius because 12 minus 4 is 8. Now I know it only looks like 4 boxes, but remember it looks like each box is actually worth 2. Oh, not 8 degrees Celsius, 8 hours, because this axis is in hours. So if we wanted to determine the rate of change, in other words, the slope, we're looking at 12 degrees Celsius, which is our rise, divided by our run, which is 8 hours. So if you do that and you put that in your calculator, 12 divided by 8 is 1.5. And because we're talking temperature in hours, the decimal is acceptable. But then what about the units? Degrees Celsius over hours? Degrees Celsius per hour. So what that means is that every hour our temperature is warming up by 1.5 degrees Celsius. If you had not included the units in thinking about this, you would have missed this unit, which is an important part of the rate of change. The next part is we're going to write an equation that represents this situation. So here's normally the equation of the line. Y equals mx plus b. And as a review, this m is supposed to be the slope, and this b is supposed to be the y-intercept. But in this case, we don't have a y-intercept because the axis is labeled big T. So we're going to say, not the y-intercept, but like the big T intercept is what we're going to do. Okay, so if we want to write this equation, we're not using y either, we're using big T. And we're not using x, we're using little t. So we're going to write the equation like this. So big T is equal to our slope, which we found here, 1.5 little t. And then we need our t-intercept. Let's think back. Did we find it? We did, right here. There's our t-intercept, negative 6 degrees Celsius, minus 6. So in the equation, I don't expect you to put the units, but if it asks for a rate of change, units are required. If it asks for the vertical or horizontal intercept, units are required. In this example, we have a cylindrical tank with 45 liters of water, and it's being drained. So we started out with 45 liters, and then we are going to like minus off a certain amount every hour. And they've given us an equation for that, and it's here. They've said that this is going to be negative 5t plus 45. So they're going to start with 45, and they're going to minus 5 liters every minute. Okay, so then they want us to make a table of values with this. So I've just copied this for our convenience. By the way, we are now on page 33. Okay, and I could put in each of these t values. For example, if I wanted to know v, I could put negative 5, 0 plus 45, and that would give me 45, and that's where I got that. Now, to save you some time, I'm pretty sure you guys can figure out how to make a table of values out of an equation. So I did it ahead of time for you guys. Okay. The ordered pair is going to be 0, 45, and then 2, 35, 4, that's 35, not 38, 25, 6, 15, and 8, 5. Okay. So if I plot this on my graph, it's going to be here, and then here. It's going to go down like this. I want to take a vote from you guys in the chat box. Should we connect the dots? Yes, we are going to connect the dots. And the reason is because volume is a continuous variable and time is a continuous variable. And because both of them are continuous variables, you can connect the dots. Okay. So then the next question asked, what is the v-intercept? In other words, where does it hit the v-axis? So the v-intercept is right here. Looks like 45. And what does the, oh, don't forget the units, 45, what is this? Okay, so the reason they put T, I ignore the T. Okay, there's a reason for it, but I won't talk about it until next semester. Really, they should put that this is in liters, right? And then this is in minutes. I should put units like that. So the v-intercept is 45 liters, and because the coordinates of this point are 0, 45, the 45 is liters, but the 0 is time. So when time is 0, what you're saying is that that's the starting point. Time is 0 is the starting point. So 45 liters in the bucket to start, at the start. So whenever you see that t is equal to 0, that means it's the starting or the initial. Okay. Use the graph to estimate the t-intercept. Okay, so the t-intercept is right here. Okay, let's just let's get an estimate for that. That's 9, 0. So it's 9 minutes, but 0 liters. So really, the t-intercept is going to be your 9 minutes. If there's 0 liters, that means that it represents the time it takes to empty the bucket. Okay, 9 minutes, and then your water is gone. Okay. So the original amount of the water in the tank is 45 liters, and it drains at a rate of, well, how many liters per minute? You can actually read this off the equation. So the equation they gave us was here, and the slope is right here, -5. So what that means is that it's 5 liters per minute, okay, and it's negative because it's draining. So it is 5 liters per minute because that's the slope. The slope is the rate of change. Okay. And there's no water left after 9 minutes. So the v-intercept is the blue, the t-intercept is the 9, and the slope is the green. and they are all important. Do not mix them up. Okay. Third example, write an equation from the word scenario. Use the capitalized variable as the dependent isolated variable. So a big hint here, if you're not sure what's dependent and what's independent, the capitalized one is going to be dependent and it's going to be isolated. Usually this is represented by y, but not here. Okay. So a canoe rental charges a flat rate of $20 and $5 per hour. Write an equation that relates cost to the time taken. Now this one's capitalized. So I'm going to make that one alone on this side. It is the dependent variable. And then you're going to put an equal sign and you're going to say the cost, it is going to be $20, but then you have to pay $5 per time taken. This is not new. Okay. The thing I want to point out here is that the independent variable is lowercase. That's a big hint as to which one's going to be which, okay? And then the dependent variable is uppercase, and it's also isolated. The other thing is the coefficient of t, this one here is the slope. And in the word problem world, the slope is the rate of change. So the rate of change of your cost is going to be $5 per hour. Okay, in this case, it's $5 per hour. And your rate of change is always going to be something per something because it's the rise over the run. Okay, let's do another example. Submarine starts at 150 meters below sea level and then descends. Descends means goes down. So we're going to be using a minus at a rate of 0.5 meters per second. So we want to write an equation that relates time to depth. But where do I start? Well, the isolated one is always going to be the capital. So you're going to start with the capital one. And then you're going to say equals something. So we start at 150 meters. And then we're descending at a rate of 0.5 meters per second every second. Okay, now I didn't put the units in the equation because we normally do not. But keep in mind, this is the rate of change, and it is the slope. And I used a minus because we're descending. We're going down, down, down. Okay. Now, some people would have written this as d is equal to negative 0.5t plus 150. That's the same thing. They're both fine. Okay. But this one looks more like your y equals mx plus b because the slope is here. See what I'm saying? And then you can see very clearly that the y-intercept is 150. That would be your vertical intercept. Okay, next one. Claire runs a small business making decorative plates. She has to pay $500 a month to rent her studio space and $10 in materials for each plate produced. Then she sells each plate for $45. Okay, here's what I want you to note here. You sell the plate for $45, but you had to pay $10 in materials. So you're really only making $35 per plate, right? So keep that in mind as we proceed here. So write an equation relating her monthly profits to the number of plates she sells. So at first, Claire is really excited. Capital P is what we start with. I am going to make $35 per plate that I sell. I've already accounted for the materials. But what have I not accounted for in my profit? So she hasn't accounted for the fact that she has to pay her rent, which is $500 per plate. Okay. So you have to subtract that off your profit because you're not making profits on your rent. Okay. And then how many plates does she have to sell just to recover the month's costs? So to recover the month's cost, it means that you're not actually making a profit. Recovering the month's cost means the profit equals 0. But remember, profit equals 0 is not the most terrible thing that could happen to you. Okay, because your profits could be in the negatives. If you didn't sell anything and you paid $500 for rent, then you are like in debt. So profit equals 0 seems bad, but it's actually not that bad. And that's what breaking even actually means. Okay, so I can calculate if the profit equals 0, what happens. So plus 500 here. So 500 is equal to 35n. So 500 divided by 35 is, so I'm getting an n of like 14.29, but obviously I can't sell 14.29 plates. So in order to really recover the cost, I'm going to call that 15 plates. And if I don't sell at least the 15, I'm not going to have recovered my costs. Okay. Now, before I move on, I do want to take a step back here because a student pointed out, but you started below sea level in this question. So should this not be negative? And actually, that's true. It should be negative. Okay, so it should be negative here because of the below sea level. It should also be negative here. Okay, so in this case, you are going to have a negative vertical intercept, which is completely legitimate. So sorry about that, but yes, it would be negative 150 below sea level. If you had started 150 meters in the air, then it would be 150 positive. I have not finished this question because the next part asks, is this represented by the p-intercept or the n-intercept? So firstly, if I wanted to figure this out, I'd have to be like, okay, wait a second. So P is here, profits, because the profit depends on the number of plates sold. And P is equal to 0, and N is equal to 15. So really, I'm like here somewhere, right? So if P is equal to 0, oh wait, no, P is equal to 0, N is equal to 15. Yeah. So I'm here. Okay, so we have a coordinate of N equals 15 and P equals 0. And that would be represented here, comma 0. Not 0, 15, 15, 0. So then in that case, then we are not looking at the p-intercept. From the sketch, you can see that this is actually represented by the n-intercept. Okay, this one. Ecologist tags a bird and tracks its movement from the field station. Because of a delay in setting up the equipment, the bird was already a distance away when the recording started. Okay. After 3 hours of tracking, okay, I'm just going to make this little chart here. So this is going to be my time, and this is going to be my distance. And distance is capitalized because it's the dependent. So it says that after 3 hours of tracking, I was like 28.5 kilometers from the field station. And then after 7.5 hours, it was 69 kilometers. And then after 9 hours, it was 82.5 kilometers. Write an equation that relates the bird's distance to the hours traveled. So it's going to be D is equal to like some kind of slope, and then T plus some kind of like y-intercept. And I don't know what either of those are right now. Okay. Now, if I had the 0 point here, then that would have been my B. But I don't even have that. So life sucks right now. But I can calculate my slope though. Okay. I can calculate the M by doing like y2 minus y1 over x2 minus x1. So I'm just going to go ahead and take this as my y2. So 28.5 minus y1. I guess I'll take this as y1 divided by x2, which is 3, minus x1. So as soon as I have 2 points, I can do this. Like, why didn't I choose the other 2 points? It shouldn't matter. You can choose any 2 points you want, okay? So 28.5 minus 69. And I'm going to divide that by 3 minus 7.5. Yeah, it's negative in the top and the bottom. But because of that, it cancels out, and your final answer in the end ends up being 9. So actually, this slope is 9. Okay, it's traveling at a speed of 9 kilometers per hour. That's how fast this bird is going. Okay, but that's still kind of unhelpful because I still don't have B. So to get B, and this comes up in your quiz as well from yesterday, how do I get B when I have like everything else? Well, do you have a point? Yeah, I've got 3. Okay, we'll pick one of them and substitute this in for 3. Okay, time is 3. Distance is 28.5. I know that this is 9. And this is B. And like, go nuts, man. Solve for B. Because if you have the slope and you have a point, you can solve for B. Okay, so 28.5 minus 27. If you solve this correctly, you're going to get that B is equal to 1.5. So do I have an equation then? Yeah, I do. I know that this is 9 and this is 1.5. Okay, so at a time of 0, the bird was already 1.5 kilometers away from the station. So what we know here is that B is 1.5. That is the d-intercept or the y-intercept. So this is 1.5. So when the recording started, that is t equals 0. Okay, how far away from the station was the bird? And that was 1.5 kilometers. Okay, and that, let me just sketch this out. So here's the time, and here's the distance. The capital letter is always on the vertical. So we found that when time was 0, d was 1.5 kilometers. Okay, so this is the d-intercept. Okay, so the next part is meant to be done on your own, where you determine the rate of change. Okay, I just want to say that the rate of change must have units on it, and it's always going to be something per something. In this case, it's going to be like kilometers per hour, because rise over run. Okay, I'm going to skip all the way to example. So this is lesson 5B, which is where we look at a sketch of a multi-leg journey. Okay, so this is a journey that starts like super fast, and then you go backwards, that kind of thing. So I'll just do an example here. Example number 4, and this is on page 36. What's happening here? So this says that this is the amount of fuel left in a car's tank during a driving trip. So it consists of 6 segments. You can see already here that it started with about 70 liters of fuel in it. And then the fuel started going down. Because from point A to point B, we are driving. So the tank is losing gas. Right? And then between point B and C, we stop losing gas. Well, how can you explain that? Well, we stopped driving. Okay. We stopped for how long? Well, from about 3 to 4 hours, we stopped for about 1 hour. Okay. And then we started driving again. Oh, wait, they didn't ask for CD. Okay, we're clearly driving here, but they asked for DE. What's going on in DE? How come I had so little fuel and then all of a sudden I have lots very, very quickly? Well, that's because you stopped at a gas station to refill. Okay, and your gas went up very, very quickly. And then we started driving again. But if you look at the slope between EF over here versus like the slope of AB over here, they're close, but clearly the red one is a bit steeper. So this is driving a little bit faster than AB. Like the rate of gas loss is a little bit faster than in the red segment. I mean the yellow segment here. Okay, so yes, you were driving here, but because the red one is steeper, you're driving faster there. So that's like pretty intuitive as to what's going on. Let's do example 5. The Hikers Club went for a walk in the park. Okay, so the first part is they traveled at a constant speed and then stopped for a break. So let's just say that they started here. What says distance for starting point? So it started here. And they traveled at a constant rate and then they stopped for a break. Okay. Then they walked backwards towards their starting point, but they walked at a slower pace. So slower pace means this better be not so steep. So I just got to make this clear that that's not as steep as the blue piece. That's not very clear at all. Like this, okay? A slower pace than when they started, but they didn't make it all the way back. But then, close to the end of the hike, they walked at a constant speed. Maybe all of a sudden they gained motivation or they realized that they had to get home faster. That was faster than their initial pace. Okay, initial pace was the blue. So if they're going home even faster than that, it better be steeper. Okay, so clearly the green piece is steeper than their initial pace, which was the blue piece. And I'll just clean up my drawing over here. Okay, so you should be able to match up graphs like this to this by saying that like the steeper pieces are faster, and like the flat pieces are not moving. And that's pretty intuitive. Example 6, draw a graph to describe each situation. So this situation is not always linear. For example, your height over time. When you were like a baby, you grew really, really fast. But now, and like as a teenager, you grow pretty fast as well. But when you get to be an adult age, you pretty much don't grow anymore. So like your growth is like really fast at first, and then it just kind of like flattens out, and then you stop growing. So this is not linear, not a line, but that I would expect you to understand that you don't grow as fast when you're an adult. What about your height above the ground as you ride a Ferris wheel? Okay, so at a Ferris wheel, you don't start on the ground, you're like a little bit above the ground. And then as you go up, you're like, I'm going up, and then I'm coming back down again. But the Ferris wheel does not scrape the ground, so I don't want to see your graph scraping the ground. This one is not, it's not got time here. It's got speed, so this is not a single journey. It says the time it takes you to walk to school is related to how fast you walk to school. So maybe on day 1, you walk really fast, and it takes you only 10 minutes to get to school. And then on day 2, you walk kind of medium fast, and it takes you 20 minutes. But then on day 3, you walk really slow, and it's going to take you 30 minutes. So the relationship between how fast you walk, like if you walk at a speed of 0, first of all, you're never going to make it. Let's say you walk at a pretty slow speed, like this is like 10 minutes, or like I don't know how fast you're walking here, but this is like, let's say that you're walking slowly. So here's slow. Okay. And then here's medium. And then here's fast. Interestingly, if you walk fast, it's going to take you less time. Right? If you walk medium, it's going to take you like more time. And if you walk slow, it's going to take you a lot of time. Right? So then basically this is the relationship, but you have to understand that this is not like it's not one journey. It's an idea of like first day, like this is how fast I walk, second day, this is how fast I walk. And the faster you walk, the less time it'll take you to get to school. That's what this graph is saying.